Now I want you to just watch this for just a second. I want to take your run-of-the-mill power function, y equals ax to the b. And I want to apply a few logs to this for no reason that'll be apparent at this moment, but let's just say that we take the log of both sides. So now I have the log of y equals the log of ax to the b. Now one of the rules from logs says if I have two things that are multiplied together like that, then I can just separate them into the log of a plus the log of x to the b. Just separate them like that. And then I can work with this part here to get this. So now I've got the log of y equals the log of a plus b log of x. And all I've done there is just apply some log rules again for no reason that's readily apparent. And it looks okay, except it's kind of confusing with all those logs. So I came up with my own little definition. I'm going to let capital Y represent the log of little y, capital A represent the log of little a, and capital B represent the log of little b. Oh, capital X could represent the log of little x for no real reason, except I think that'll make my life a little easier. So over here where it says the log of y, I'm going to write a capital Y, log of a, capital A, and then I've got a little b and a capital X. Now the reason that this is so nifty is this looks linear. This function up here, of course, was a power function, but now I've tricked it into looking like a linear function. But it's not a linear function between x and y, because that would look like this, y equals a plus bx. This is a linear function between capital Y and capital X. Okay, that's fine. That means if I was going to do, say, linear regression, I would do linear regression on capital X and capital Y. Or linear regression on the log of X and the log of y. Now, when I got that equation, if I did linear regression on log of x and log of y, so for example, maybe L1 had my x's and L2 had my y's, maybe L3 needs to have the log of my x's and L4 can have the log of my y's. So now I'm going to do linear regression on these two lists. So my calculator is going to report to me y equals a plus b to the x, whatever those are. But I'm smarter than my calculator. So I know that what it really meant was the log of y equals a plus b log of x. And in fact, I'm even smarter than that, because I know there should be a little hat right here. Okay, fine. Now let's anti-log both sides here. And I guess to be consistent with what I've done before, it would be helpful to you that really that's the log of a is what it's given me there as well. So if I anti-log both sides, that's a fancy phrase for 10 to the. If I 10 to the on both sides, then the left side just becomes y hat, and the right side becomes 10 to the log a times 10 to the b log x. Now, this part will cancel. So now I have y hat equals a And then over here on this part, I'm going to use one of those rules of logs to make this 10 to the log x to the b. And now again, my 10 and my log will cancel. And so I end up with y hat equals a x to the b. Aha! The power function. Now that's no surprise because all I did was log it and then anti-log it, but I took a function that was a power function, I tricked it into looking linear, and then I turned it into a power function again. This will prove very useful. I know some of you want to take notes. Hang on, we'll come back to that. Let me show you now what an exponential function would look like. So an exponential function looks like this when it's got the x and the exponent. And I want to do the same idea. I want to take the log of both sides. So I take the log of both sides. Because we know, of course, that an exponential function looks like this. It doesn't look at all linear. And then, just like before, I want to split up this on the right to make it the log of a plus the log of b to the x. And then that's going to be the log of y equals the log of a plus x times the log of b. And then I'll use the same clever notation I used a second ago to turn these into capital letters. Y equals a plus x b. Now that bothers some of us because b is a constant and x is a variable. So if you don't like that, which I get, you might not like that, you could go ahead and flip the order of that and make it y equals a plus bx. Either way, now what I have, again, is something that looks linear. But if I did linear regression, I would do it on x and the log of y, because I have a little x and a capital Y. Notice before, when I wanted to do that linear regression, I did it on log of x and log of y for a power function, a function like y equals 3x squared. But on a function that looks like y equals 3 times 2 to the x, an exponential function, I want to do linear regression on x and the log of y. So let's see again what would happen if I started out with that. So I did linreg. My calculator told me something like y equals a plus bx, but I remember that what I actually plugged in was something a little bit different. So I've got to put my logs back in here. It was really the log of y equals the log of a plus b log x. Oh, I didn't write. Back that up just a bit. X log b. That's the way it was here. So when I anti-log both sides, I get 10 to the log of y equals 10 to the log of a times 10 to the x log b. On the left side, the 10 and the log cancel out to give me a y. On the right side, I get a times 10 to the log b to the x, which is y equals a times b to the x when the 10 and the log cancel. And again, I've got an exponential function. Now I know that was fast and furious. The thing I wanted you to see is going through how we could take functions like a power function or an exponential function, use logarithms, and trick them into looking linear. I've written all of this up for you in a document on my webpage. The URL will be in the description of this video if you want a hard copy of it. Also, in the description of the video, I have a link to the next video, which will show you how this could be put into action.